Good morning, everyone. We're going to get started this morning back in chapter 4. So we're just about at the halfway point of the chapter. We were on this slide at the end of class on Friday. We were trying to write the net ionic reaction for some acid-base reactions. So when acids and bases react together, they form a salt or an ionic compound plus water. And so we're really almost doing the same idea of a metathesis reaction. We're just exchanging the cations, or you can think about exchanging the anions and seeing what products we can make. And we end up making water, which is the main driver of this reaction, because when H plus and OH minus collide together, they form a molecule that doesn't then back dissociate and allows this reaction to take place. And this is one of those 100% yield. This isn't an equilibrium reaction. This reaction takes place very quickly. Essentially, as soon as H plus and OH minus collide together, they're going to be, forming water and not going backwards in this problem. But our KCl product is water soluble, so we get our, K plus and Cl minus in solution. Our thought on ionization, our thought of going from that full molecular reaction, which is the first one here, then we call that the full molecular reaction, because we're writing HCl and KOH as if they were molecular, even though they're not. KOH is really not KOH in water, it's really K plus and OH minus. We have to think that KOH is a strong electrolyte, and it really, therefore, is in its ionic forms in solution, K plus and OH minus. HCl is also a strong electrolyte. It's a molecular compound, but it's a strong acid. Strong acids fully dissociate into H plus and the counter ion Cl minus. And so HCl is really H plus and Cl minus in solution. And so H plus, OH minus bump into each other, form water in this reaction. K plus and Cl minus stay in solution, and we cancel them out as being spectator ions. So we call the K plus and the Cl minus, they're spectators. So the spectator ions just watch the reaction. They don't change form during the course of the reaction. They don't disappear, they're still there, but we can cross them out from the net change in the reaction. So our net ionic reaction is down below. And then the middle reaction is what we might call the full ionic reaction. It just shows everything in its ionic form. So we have the full ionic in the middle. And so then we did this also for the reaction of HF. Now the difference between HF and HCl is HF is a weak acid, therefore weak electrolyte. So HF doesn't fully dissociate in water. So if you have a solution of HFAQ, that would still contain mostly intact molecules of HF. So we don't dissociate HF into our full ionic equation. So even though the equation is called the full ionic reaction of the full ionic equation, we don't ionize everything. We only ionize the strong electrolytes. So we only ionize the strong electrolytes, so we leave HF intact. KOH is a strong electrolyte, so we dissociate it. KF is a strong electrolyte. Anything containing potassium is water soluble. All water soluble ICs dissociate. So the thought process on a compound, is it molecular or ionic? KF is ionic, therefore it's water soluble because it contains potassium. Being water soluble, ionic compound means it's a strong electrolyte. So we dissociate it into the full ionic equation. Here we only end up with one spectator. So the spectator here is just the potassium cation. Okay, so then our net ionic equation here would just be HF plus OH minus goes to F minus plus water. And then I'm not writing AQ tags on everything that's ionic. So all the cations and anions, I've left off the AQ tag. So we should be writing AQ, or I could write AQ after all the pluses and minuses, but it would just complicate the slide. So we can imagine all of our cations have their own little water sphere, is what that means. Okay, now let's also make note that this reaction here also goes to 100% yield. If we have a acid and base, they're going to fully react together as long as one of them is strong. So I just need either the acid or the base to be strong, and the other one can be weak, and the reaction will take place to 100% yield. If you took a weak acid and a weak base and react them together, that's actually a very interesting equilibrium problem that you'll see in chapter 16. So you'll revisit that problem later. So as long as you have either the acid or the base be strong, in this case KOH is a strong base, water-soluble ionic compound that contains hydroxide, anything making hydroxide is a base, KOH makes a lot of hydroxide ion, therefore it's a strong base, because we get the complete ionization to hydroxide. Now let's push into some slightly more complicated reactions, phosphoric acid's a triprotic acid. We can react that with KOH. You can actually do this in what's called a titration. We'll see that a little bit later, where you can imagine adding KOH dropwise, and then the acid will slowly react. And so if you add KOH dropwise, the first H plus will fall off. You'll make H2PO4 minus. If you keep adding KOH, eventually you'll make HPO4 minus. If you keep adding KOH, eventually you'll make phosphate ion and go the whole way and lose all three of those H plus ions. So the key is kind of thinking that this thing here is triprotic. So KOH is capable of pulling all of the acidic hydrogens off of a compound. So this should take the H3PO4 all the way to PO4 3 minus, and then we swap the H plus out with K plus, so it'll form K3PO4. So we're just balancing out our charges. So we get K3PO4 for our molecular compound ionic product, the IC or the salt that forms in this reaction. And then we form water. And so we're taking 3 H pluses, so we're going to need 3 OH minuses, so we're going to get 3 waters. Okay, so we're neutralizing the H plus. We're pulling the H plus off with the hydroxide ion. So this problem's a little bit different than the HCl problem. HCl was really H plus OH minus collide. They make water. Here, you're going to have OH minus hit an H3PO4, another OH minus hit the H2PO4 that remains, another OH minus hit the HPO4 minus, HPO4 2 minus that remains, and eventually get to the phosphate ion. So we add 3 parts, like 3 moles of KOH here for every mole of H3PO4 to end up forming that 1 mole of K3PO4 and 3 moles of water. Now K3PO4, water-soluble compound because it contains potassium ion. So anything with K plus is water-soluble. It's an IC, therefore it's a strong electrolyte. So my strong electrolytes are the KOH and the K3PO4. I have a weak acid, weak electrolyte. Now, how do I know that? H3PO4 is a weak acid. Well, it's not one of the 7 strong. So it's not one of the 7 strong acids. And so my net ionic equation, or if I'm going towards my full ionic equation, so let's write the full ionic. So we have H3PO4, AQ, plus 3K plus 3 OH minus, goes to 3K plus PO4 3 minus. All those big ions we learned how to name in chapter 2 stay intact in water, so that's how I'm picturing phosphate from nomenclature, so that it stays intact here as PO4 3 minus. And then my 3 waters stay intact because water is a non-electrolyte. So water is a liquid. Again, I could put AQ tags for all the ionic species, but I just leave the, anytime I have an ion, it has to be dissolved in water. So of course our ions are AQ, so I'm just neglecting writing, all those AQ tags. Then I only have one spectator, that's the K plus. And so then my net ionic equation would be H3PO4 plus 3 OH minus goes to the phosphate ion plus 3 waters. Now, there's only one weak base that we really expect that you recognize. We mentioned that there's others that truly exist, but in terms of easy recognition at this point in our chemistry backgrounds that you guys have, H3PO4 is kind of our prototypical weak base. It's a weak electrolyte. But here we can imagine that H plus is going to form, it's going to like either pull or take the H plus from the Cl minus. So we'll form NH4 plus. So we add that H plus onto the NH3 formula, make ammonium, and then chloride ion. And now if you want to go full molecular, you can say ammonium chloride as a compound. Whenever I lasso out, I'm just trying to show that you obviously don't write the charges in with the formula. So the formula would be NH4Cl. That's a water-soluble compound because anything with ammonium is soluble. Chloride doesn't have illicit exception of the ammonium cation. And so if the ionic equation would look like H plus Cl minus plus NH3AQ goes to NH4 plus AQ plus Cl minus AQ. So I guess I'll write all the tags in on this example. So H plus AQ, Cl minus AQ, plus ammonia goes to ammonium plus chloride. So what's the spectator here? Just the chloride. So our net ionic would be H plus NH3 goes to NH4 plus. And again, both of these reactions on this page would go to 100% yield because we have either a strong acid, weak base in the bottom example or the weak acid, strong base example in the top reaction. So as long as one of the acid or bases is strong, then we know the reaction goes to 100% completion. If they're both strong, of course, that would also go to completion. The only time we don't know for sure is if we took like HF plus NH3, we wouldn't know if that went to completion. It's an interesting equilibrium problem, but not a question that we'll tackle in this class. So just one last slide on acids and bases, or that you can have other types of ways of leading an acid-base reaction to go to completion. If you're noticing, like the sort of messages, you need something to form in a reaction that doesn't like back dissociate. So like our precipitation metathesis reactions required us to form a solid, because if you recall, for those reactions we had soluble ionic compounds that we're mixing together, and if you just made soluble products, nothing really changed. You needed to have something form like a solid that drove the reaction to take place. That's the same idea as water forming. We take H plus, OH minus in some form, allow them to collide together or allow them to form water, and then water doesn't back dissociate. You can also form gases. And so if we were to take H plus and Cl minus from HCl, react them with a carbonate, say in solid form, the calcium carbonate would dissolve in acid to form calcium 2 plus. We keep that charge state of calcium and the 2 plus. And then we end up making H2CO3 in the process. If you think of the H plus ions forming with carbonate, we make H2CO3. Well, H2CO3 carbonic acid is actually not stable in water. If we make H2CO3 in water, it rapidly dissociates into CO2 in water. This is why things like carbonates or hydrogen carbonate ions are used in cooking, because they make a gas if they form the acid H2CO3. So if you imagine trying to form the formula H2CO3, we just get the rapid dissociation into CO2 and water. So carbonic acid itself is not stable enough to exist in water. So if you imagine, the two H pluses forming the H2CO3, it just decomposes into the gas. And then that, of course, drives this reaction to take place, because as soon as the CO2 forms, it floats away, and then you can never go backwards. So things that allow reactions to take place are things that form that can't go backwards. So like solids, like water, like gases here. So it's that gas formation that allows this, CO2 to float away and then never go backwards into the reactants. We can take hydrogen carbonate ion. This is more commonly used in like baking soda and cooking, for example. So if you take the HCO3 minus ion, it can react with an acid like HBr. HBr is a strong acid. And so then you can also form H2CO3, which then rapidly dissociates again into CO2 and water. And so then you can form or have a reaction take place like this one here, again, where you're having CO2 form, leave the reaction, never go backwards to reform the reactants. So both of these reactions, of course, 100% yielding reactions. We can also form like hydrogen sulfide, the smell of rotten eggs, by taking a sulfide like sodium sulfide, reacting with an acid like H2SO4, and then the two H pluses combined with the sulfide to make H2S, and then you're left behind with sodium sulfate. And again, H2S turns out to be a gas at room temperature, can float away from the mixture, would smell pretty bad, but then again, drives the reaction to taking place. So just wanted to mention that, things that drive these exchange reactions to taking place are forming solids, forming water, or in these cases, forming a gas. And let me extend the 100% yield, so that reaction also would yield 100%. And the reason why I'm noting the yield here is because we talked a little bit about weak acids, weak electrolytes, weak bases having partial reactions that only go to like less than 10% yield. That almost all the other reactions that we're talking about are metathesis reactions, go to 100% yield. Our acid-base reactions here are going to 100% yield, just like these ones here. So just want to kind of contrast equilibrium reactions, which are where we just have a single weak electrolyte partially dissociating, is where you get a partial reaction. All the other reactions we're looking at here are ones that are going towards 100% yield. All right, so the middle section, or like the section 4.4 in the textbook, is on the topic of oxidation and gets into what we call oxidation reduction reactions. It begins with the discussion of oxidation numbers. So let's get into like how we can assign either the charge for an atom in an ionic compound, or then also how we can assign charges, or what we call oxidation numbers, like a bookkeeping system of charge, to atoms within molecular compounds as well. So whenever we're looking at compounds and trying to figure out their oxidation numbers, ionic compounds are actually very easy because their charges are just the charge of the atomic ion that we've been writing all along. So atomic ions have oxidation numbers just equal to their charge. So for example, if you have calcium chloride, that we know that it's a calcium 2+ and a Cl-, and so these are also the oxidation numbers. So the oxidation number of calcium is 2+, just like its charge. The oxidation number of chloride, or the chlorine atom in CaCl2, would be -1, just like the charge here is -1 for chlorine. So charge of atomic ions is exactly the same as the assignment of the oxidation number. So oxidation numbers in some ways are the charges of the atoms in ionic compounds, but then when we look at molecular compounds, it's more of a bookkeeping system. So when we get into molecular compounds, like for example, if I write water, and I start writing and say, well, what's oxygen's oxidation number? Well, generally, oxygen's oxidation number will be -2, with the exception of peroxides, which we saw that O2, 2-, their oxygen's net oxidation number would be -1. It's that -2 charge over the 2 O's. So we're just taking the -2 charge, dividing it by the 2 O's to get -1 overall. Superoxides, that O2 with the minus charge, those are the interesting case of where we have a -1 charge for 2 O atoms, so the charge is actually fractional. So our oxidation number per each O is -0.5 for superoxides. And then if we have compounds with fluorine, fluorine's always going to be negative in compounds. So when fluorine is in compounds, its oxidation number will be -1 always. So that's down here. So fluorine's always -1 in compounds, and other atoms have to adjust accordingly off fluorine being -1 in compounds. So let's look at we're going to have to look at a lot of examples to kind of see how these rules work, but let's kind of start piecing this together. So what we're saying for oxygen is, as long as it's not a peroxide or superoxide or a compound with fluorine, its oxidation number has to be simply -2. And so water here, that's not an O2, there's not even a second oxygen, there's no superoxide, there's no O2 in the formula, so I know it's not a peroxide or superoxide, and obviously hydrogen isn't fluorine. So that means oxygen has to be in that ordinary -2 oxidation number. Now, the charge of O2 is really not -2 here. Like, this really isn't an oxide ion like it is with sodium. If I have Na2O, if I contrast this with the ionic compound, here, this is a very specific representation. We haven't gotten to Lewis dot structures yet, but this is what a -2 charged oxide ion looks like. Sodium would be like this, like a cation. We might have another sodium next door. So we might have our sodium cation here, oxide ion here. Well, water doesn't look quite like that, even though we're going to assign it with the same set of oxidation numbers. Hydrogen's oxidation number rule is it's +1 when it's in a compound that's molecular, and -1 when it's in an ionic compound. And we'll contrast that in a minute too. But let's just look at here the molecular compound water, +1. So this is not like this. Like, this is not the picture for water. So even though we assign the same oxidation numbers, -2 and +1 and Na2O, as we would water, plus and -2 for H and O, that water still will look like the structure like this, where we have these covalent bonds linking the atoms, but the minus charge is going to be reflective of what the partial charge ends up being on oxygen. So we were already talking about this a little bit at the beginning of the chapter on how water has a partial negative charge on the O, so the O is what surrounds the positive charged cations. The hydrogens bear the slightly positive charge, so the hydrogen end of water surrounds the negative ions in the solution process for something like sodium chloride or any of our ionic compounds. Now, water doesn't bear the full charges. But the oxidation numbers help you see that O is the more negative atom, H is the more positive atom in the compound. We'll get to electronegativity and Lewis structures and predicting, where these charges lie in molecules later. But the idea of oxidation numbers is it's a bookkeeping system for charge. It's not necessarily the actual representation of charge in compounds. So oxygen's charge really isn't -2 in water. Its oxidation number, though, is -2. Let's contrast that hydrogen rule here for molecular versus ionic. So when is hydrogen in an ionic compound? Well, if you recall, hydride is H-. And so if I take something like calcium, like Ca, I can form calcium hydride with the formula CaH2. So that's calcium hydride. And here the oxidation numbers work out that calcium's in its ordinary +2 state, +2 charge. So +2 oxidation number, hydrogen minus to counterbalance. And so that's the hydride ion. So hydrogen -1 in ionic compounds as its oxidation number, +1 in molecular compounds. We mentioned fluorine's -1 in all compounds. Now let's mention a detail to make sure we're clear. If we have molecular fluorine, like F2, like elemental fluorine, F2's oxidation number here would be 0. If I have sodium in its elemental form, sodium solid, that's the oxidation number of that would be 0. So elements, even in formulas, would have oxidation numbers of 0. So if I have like O2, the oxidation number of oxygen in O2, this isn't a compound. So if I have molecular O2, the oxidation number would just be 0. So elements have 0 oxidation numbers. When they form compounds, they then pick up their, we then look at the sort of system to assign their charges. A compound with O that contains fluorine is F2O. This is probably on the next slide. There's a bunch of examples on the next slide that we'll go through to try to nail down these rules. But the idea would be I can't start with the O because it's in a compound with fluorine. So oxygen's usual role is -2, except if it's in a compound with fluorine. Fluorine's always -1, so there's 2 of them. So my total oxidation number for the oxygen here has to be +2. So oxygen goes positive, and this compound would bear the positive charge. Fluorine's negative. The reason why comes up later in chapter 8. It has to do with relative electronegativity differences. You probably learned about electronegativities. Fluorine is the most electronegative element. It wants electrons more than oxygen, therefore keeps that negative charge. And then all of our other atoms we can, determine by deduction. So if we have an atom we don't recognize as being a halogen, as being oxygen or hydrogen, or an ionic compound where we know the charges based on the periodic table, we'll have to be able to pick those up by deducing the charges from the other atoms. Okay, so a bunch of examples on this slide here to try to nail down the rules. So again, elements are 0. So anything in elemental form is just 0. So I'm just looking here, these are all elements in their, what we would just call elemental forms. Those, in the case of like H2 and Br2, are molecules, but they're not compounds. So whenever we just have pure elements by themselves, just 0 oxidation numbers. Now, a lot of the next row are things that we can look at just based on the periodic table placement. Like aluminum, we know that the charge, going back to chapter 2, of aluminum should be +3. We know oxygen's in its ordinary -2 because it's not a compound with F, not a peroxide, not a superoxide. A little like asterisk on peroxides and superoxides. There's a couple on the page on the 3rd row. But peroxides and superoxides only form with alkali and alkaline earth metals. They don't form with like transition metals. They don't form with aluminum. They can form with hydrogen. We'll see hydrogen peroxide. We've probably seen that name used before. But in the case of peroxides and superoxides, you should be able to recognize them because they'll be paired up with like a group 1 or a group 2, not something like aluminum. So sometimes we get confused. Could this be a peroxide or superoxide? It can't be with aluminum. Okay, so just to show the balancing of charges, 6+, 6-, charge neutral. This goes back all the way to chapter 2. So the assignment of charges are the oxidation numbers. So the oxidation number of aluminum +3, oxygen -2. Calcium nitride. It's basically the reverse where we have a 2+ calcium from the periodic table placement, nitride, and its ordinary -3 charge state. That works out because I have a 6+, 6-. In fact, let's make nitrogen unclear on what it is. Like, let's even assume we don't know it's nitride. The way we can deduce that it's nitride is we know calcium can only be a +2, so there's a +6. So we have to have a -6 from the nitrogens to counterbalance the charge, because the overall charge for a compound has to be neutral. And so there's 2 nitrogens, 6 divided by 2 goes to -3. So we can deduce that charge on nitrogen if we forgot that that was a nitride ion. Calcium's ordinary charge is +2. Sulfur, therefore, the balance has to be a -2, which makes sense because sulfur is in the row of oxygen, so the ordinary charge for sulfide is -2. So we see another example of a hydride here. Barium's in the alkaline group, so it's a +2 charge. So just based on periodic table placement, barium's a +2. So therefore, our 2 hydrogens have to be +2 divided by 2, or excuse me, -2 divided by 2 for -1. So that's another example of our hydride. So another example of a compound containing fluorine is O2F2. Now for O2F2, again, think about how we'll start with fluorine, because that's the one that always has to be -1 in compounds. So fluorine's oxidation number is -1. So there's a -2 for the 2 fluorines. So the 2 oxygens have to share the +2 charge. Therefore, the deduction of charge for oxygen in O2F2 would be +1. So O2F2, probably not the most common compound, but for that formula, we could deduce that the oxidation number for oxygen would be +1. Now, is O in O2F2 really +1 charged? Probably not, but it should be the atom that bears the overall positive charge, would be the idea. The next 2 examples, KO2 and CaO2, get at the peroxides and superoxides. Now, the way we can deduce these 2 compounds' charges is we know potassium's a +1, group 1, calcium's a +2 because of periodic table placement. And so then by deduction, the KO2 has to be the superoxide by nomenclature. So if we recognize that as potassium superoxide, then we know that that's the O2- ion. We can deduce that off the charges, so the 2 O's have to share the -1 charge. So the overall oxidation number has to be -1/2. So +1 -1/2 times 2 equals 0. So we have to just make the overall compound charge neutral. So CaO2, again, a +2. Our 2 O's have to be -2 to go to overall charge neutral. And so the 2 O's share a -2 charge or oxidation number. So we divide the -2 by 2, we get -1. So it's just algebra. So we're just trying to deduce what charge here for the O balances out the +2 of calcium. So it'd be -1, so we go 2, -2 times 1 to go neutral. Now we can outthink ourselves a little bit here. What's the charge of oxygen in CO2? Or what's the oxidation number of oxygen in CO2? So sometimes we confuse ourselves into, is this a peroxide or superoxide? Again, the peroxides and superoxides, so the O2, 2-, O2-, these only form ICs with the alkali and alkaline. And then we'll get the MC with H. So like we can make H2O2. The superoxide, not so common. Superoxide's a pretty rare anion. But we can make like hydrogen peroxide. So we'll show that in a moment. But for CO2, what I want to have a thought is that it can't be a peroxide or superoxide. We're not, carbon's not an alkali or alkaline. It's not hydrogen. So this just has to be the ordinary -2 oxidation number for oxygen. So oxygen's weird. It can have different oxidation numbers, but we just have to kind of be clear on looking for peroxides or superoxides, which should be really, clear because they come from a group 1 or group 2 metal, and we can deduce the charge from that charge, or perhaps with hydrogen, and then that's going to be it. So this is just an ordinary -2, 2 of them for a -4. So this is a +4 oxidation number carbon in CO2. And let's do H2O2. Just to make sure to hit this for how do we know that's a peroxide? How do I know that's hydrogen peroxide if I didn't know already? Well, by ordinary rule, hydrogen should be +1 in a molecular compound. This is, of course, a molecular compound. And so then I have a +2 from the 2 hydrogens, so therefore I have to have a -2 across the 2 O's, which is what we call the peroxide ion. And so then the per atom oxidation number would be -1. So oxidation numbers obviously are the charge or the oxidation number per single atom, and then we're just doing the math below. So I write the oxidation numbers up here, and then I do the math that I need to do to work it out down below, just to kind of separate the doing of the math of assigning the, so we have to account for the 2 hydrogens, the 2 oxygens to work out overall charge neutral. So we're just doing the +1 times 2, the -1 times 2 down below here. Just trying to get the difference between the oxidation numbers up top and then doing the math to balance it all out down below. So MnO2, can that be a peroxide or superoxide? It can't be, because that's a transition metal. And so oxygen just has to be just like with carbon, an ordinary -2. So -2 times 2 is -4. So by nomenclature, that would be manganese 4 oxide. Now what about the CuClO4 too? Looks really tricky, right? But we just have to break this down. Like, what is the charge of ClO4 minus from nomenclature? So ClO4 is at a -1, -2, -3, just a -1. So we have to go all the way back to nomenclature to get that ClO4 minus, that the charge there is -1. Once we know that that's a -1, that's where we get copper's charge. The copper is the +2. Since there's 2 of these here, that makes copper a +2. So if I want copper's oxidation number, I just have to have, the memory of ClO4 is a minus charged ion. So that gets me copper's oxidation number. Now oxygen should be a -2 because it's just the ordinary oxidation number of oxygen. It's not a peroxide, superoxide, or compound with fluorine. So -2 for O. Now I can either do the math kind of separate on ClO4. Like I can take one of the ions over here and do the -2 times 4 is -8. Now the overall charge goes to the charge on the ion of -1. So the sum of the oxidation numbers goes to the charge of the entity. So like any of the above examples, like CO2. CO2, we were taking the math on carbon plus the 2 O's to 0 because CO2 is uncharged. ClO4 minus has a minus charge. So that's why if we're summing up the oxidation numbers of just one chlorate or one perchlorate ion, we have to do the oxidation number of chlorine -8 go to -1 because that is an ion that has an overall minus charge. And so that would put chlorine at a +7. So +7 -8 being -1. And so that's one way we can get the oxidation number of chlorine to be +7. I can do it within the CuClO4 formula as well. So I could have arrived at the same oxidation numbers here with the formula, but I just have to account for the fact that there's really 8 oxygens. So there's 4 times 2. So if I'm working out my charges here, I'd have +2, and then plus whatever the charge is on the oxidation number from the chlorines, and then -2 times 8 is 16. Now CuClO4 is overall charge neutral, so that goes to the neutral charge. So the sum of the oxidation numbers has to go to the charge on whatever the formula is. CuClO4 is uncharged, so that's why that's 0. All the other above examples were also neutral. That's why we summed all the oxidation numbers to be neutral, accounting for each atom. And do you see then that this makes, let me go red just to make this clear here, that the chlorines have to be +14 to go to overall neutral for the molecule. So +2 + 14 - 16 would be neutral. So I'm just deducing, what does this number have to be here to make this math go to 0? And then there's 1 times 2, so there's 2 chlorines. So I just divide that by 2 to go to +7 for chlorine. So 2 ways I can get at the chlorine's charge, either from the full formula, where I have to account for all the atoms in the formula, or I can just separate it into one chloride ion and get the exact same oxidation number. So if you notice, we get the same oxidation number either way. So no matter how you think of the oxidation number rules, they should give you the same charges both ways there. ClF3, what's the rule there? Like, where do we start? You got to start with the fluorine, right? Because it has to be -1. That's a compound. 3 of them -3. And so chlorine has to be +3. So again, we assign oxidation numbers per atom, and then by the math, accounting for all the atoms, have to balance out the oxidation numbers to the charge in the molecule here to neutral. CCl4. Now, the previous rule on the previous slide said for like halogens that they're usually -1, like Cl, Br, and I are -1, except when they're paired up with fluorine, where fluorine goes -1. Well, here, chlorine should be its ordinary -1, 4 of them -4, so carbon goes +4. So we started here with the -1, and then 4 of them for -4 to get the +4 for the carbon. All right, pretty dry topic, pretty boring. I put half the room to sleep here. Oxidation numbers are just a set of rules. We got to do several examples to really nail the rules down, but they're really not the hardest of rules. It's just doing a few examples between now and next week to make sure we have this down pat. Now, how we can use oxidation numbers is to help us see if a reaction is or is not a reaction that changes charge. And so an oxidation reduction reaction is where we have electrons being lost by an atom, that's oxidation. So losing electrons is oxidation. And then atoms that gain electrons are reduced. So gaining electrons is reduction. In a chemical reaction where we have oxidation reduction going on, it's a tandem process. So one atom loses electrons, another atom gains them, so that they're not just lost or gained out of the ether. So we have electrons going from an atom to another atom so that we're not losing or gaining electrons throughout the course of the reaction. And then the idea would be, can we identify if atoms are reduced or oxidized, and identify which of the atoms are reduced or oxidized, so we can know if the reaction is an example of this oxidation reduction reaction. So as an example, H2 plus O2, so 2H2 plus O2 goes to water. We know that's that balloon reaction we did on the first day of class. Here we have elements, so those should be charge neutral in terms of their oxidation numbers, so 0 and 0 for H and O, and H2 and O2. And then in H2O, we get our +1 and our -2. So this would be an example of an oxidation reduction reaction. Sometimes we call it a redox reaction. So you'll see this also called redox. Is another synonym for this type of reaction. So this is a redox reaction because we have one of the atoms gaining electrons. So which atom gains electrons? Is it the H or the O? The O gained 2 electrons. Each O atom gains 2 electrons to go to the O2 minus oxidation number. So we're just picturing neutral O to -2. So the O was the atom from the reactants that gained electrons. Therefore, that's the reduced atom. So oxygen is reduced. The hydrogen here is the atom that lost the electron to give to the O. So the H goes from neutral to +1. So that's hydrogen losing an electron. Losing electrons is oxidation. So the H is the oxidized atom. Now, I almost hate to do this, but I'm going to mention this here. I don't think you'll see this necessarily. I don't think we test this per se, but it's a nomenclature I think that's useful to see here, that we actually call O2 the oxidizing agent. And then H2 here would be the reducing agent. I guess we do this just to confuse you guys. Like, I don't know why we do this. But if we think about this here for a second, the O atom, and usually what we do is we look at per atom, like which atom or like which element is the element that's has lost electrons like H and was oxidized during the course of the action. Usually we look per element. What's the element that had undergone the gaining of the electrons? In that case, in this reaction, it's the O. And then when you look at the agent, it's like the facilitator of that in something else. So like O2 facilitated H's oxidation. So that's why you call O2 the oxidizing agent. So the oxidizing agent is itself reduced, or an atom within it was the one that has undergone reduction. And then usually you call the agent, you look at the entire substance. So you usually look at like O2 in gas form. Usually you're defining the agent as the substance that contained the atom that had undergone reduction. And again, I just want to introduce this nomenclature here. You'll probably see it next semester. I just want to introduce the word agent is the facilitator of something else's act. So by the hydrogen being oxidized, it allowed something else to be reduced. So that's why we call hydrogen the reducing agent. Now, one thing I'll give you for the word agent here, think about how like a sports agent or a movie star's agent, like the agent for a movie star usually themselves is not a movie star. Usually the sports athlete's agent is not themselves currently performing athlete, so they facilitate the other person to be like the athlete or the actor. Okay. So again, I just want to introduce the word agent, just I guess to confuse you guys, but you might see it every now and then. You might see it next semester. I just wanted to introduce the idea that it kind of goes opposite, that the oxidizing agent has an atom in it that was reduced. The reducing agent is the one that has an atom in it that had been oxidized because they facilitated that action in the other substances in the reaction. Okay, now let's get back at using the idea of oxidation numbers to help identify if a reaction is an example of a redox reaction. So lead's an elemental form, so it's 0. H is plus. Oxygen and nitric acid would be -2. The nitrogen in nitric acid should be +5 by deduction. So I get +5 just to equal 0 for nitric acid. And so lead's going to lead 2+. How do I know that? Because nitrate's a minus. So lead 2+ being formed. And then the nitrate and the oxygen actually stays the same. So NO3 with a minus charge. So we would have -2, or -2 times 3 for -6. So a +5 for nitrogen. So nitrogen hasn't changed. It was +5, it's still +5, so that's unchanged. And then hydrogen is now 0. So hydrogen has hydrogen gained or lost reactions that go to +1 to 0. To identify oxidized reduced, you look in the reactants and you look to see H+, the hydrogen with the plus oxidation number going to hydrogen neutral. That's hydrogen gaining an electron. So H is the reduced atom. And then lead is the other atom that had undergone a change. So lead had gone from lead 0 to lead 2+. So 0 to 2+ has lost electrons to get that charge. And so losing electrons is oxidation. So it's oxidized. That's not how you spell oxidized, though. Oxidized. That's not how you spell it. No, that is right. Forgetting how to spell words. So that lead is oxidized in the reaction. So losing electrons, oxidation. Leo the lion goes grr is one moniker people usually remember that it's the losing electrons is oxidation, gaining electrons is reduction. Now the other one is what oil rig is the other expression people sometimes remember. Oxidation is losing electrons, so oil, rig, reduction is gaining. So you just have to remember which one's which. The agent words, we won't probably come back to this again, but just remember if you apply the word agent, it just flips it. Okay, so metathesis and acid-base reactions turn out not to be redox reactions. So I just like to come back to the opening reactions in this chapter and just point out that when we have something like silver nitrate plus minus nitrate plus and minus for the Cl, nitrate has the same nitrogen oxygen charges as above. But then when we form AgCl, KNO3, that we haven't actually changed charge state. So I like to revisit our metathesis reactions to see that there was no change in charge going on, so not a redox reaction. Same thing with our acid-base reactions. If we break oxygen down into hydroxide ion, we would have -2 for the O, +1 for hydrogen. So we don't have any change in oxidation number going on in our acid-base reaction either. So just to point out that acid-base reactions are not redox reactions, metathesis exchange reactions are not redox reactions either. Now, can we predict when redox reactions will take place? We actually can. So we can look at an activity series and see that the relative ease of oxidation is highest at the top of the chart, which kind of makes sense because rarely in nature, in fact, I don't think you ever encounter lithium or potassium in nature because they're so likely to be oxidized into lithium plus and K plus that the elements at the top of this chart are so much more likely to be found in nature in their cationic forms, in their oxidized forms. If you look at the metals towards the bottom of the chart, they have such a low propensity to be oxidized that you usually encounter them in their metallic forms, in their solid neutral forms in nature. So things like copper, silver, mercury, platinum, gold, etc. Or that if you have them in their solid forms, they're not likely to undergo dissociation into their cations, which is good because if you have a copper pipe, you'd like it to stay copper and to not dissociate and fall apart and disintegrate. So the things at the bottom of the chart here we often call the coining metals, or just more precious metals that you can make coins out of that last and they don't dissolve, and things like water or solution. The atoms at the top are usually more reactive. The metals are reactive because they're more likely to form their charge states. And so we can use this chart to help predict when we can take a metal, or if you notice there's one nonmetal on the chart, hydrogen, that links up to acid to H+. Like, can we take metals and dissolve them in acid? Or can I take a metal and dissolve it in a solution of some cation of some other metal? I can use my activity series. So let's take a look at an example where we can kind of think of which reaction will take place spontaneously. So will copper dissolve in zinc solution? So if I have copper solid, will it react with zinc 2+, or will zinc solid react in copper solution? So let's think about how this would go here. So let's think about the first one. So if I take copper and I put it into a solution of zinc cation, do you see the problem of copper reacting is it's not more reactive, it's less reactive than zinc. So it's going to be hard for copper in a zinc solution to form copper 2+ when zinc goes back to the more reactive zinc solid. So it seems like my copper is not going to dissolve in the zinc solution. Let's think about the other reaction. So let's think about the sort of related reaction where we take the zinc solid into a solution of copper cation. Can zinc go to zinc 2+ and then copper go back to the lesser stable copper solid? That should be the reaction that takes place. So if I take zinc solid and then plus copper sulfate, CuSO4AQ, which is copper ion sulfate water-soluble ionic compound, that this here should form zinc sulfate, aqueous, water-soluble sulfate, not one of the 4 exceptions that are insoluble for the sulfate ion, and then we form the copper solid. And then my thought here is the reactant needs to be more reactive than the product that we're forming. Like, I have to start with something more reactive and produce something less reactive. That's how most reactions go. We start with something at the top of the hill and produce something at the bottom of the hill. And that's exactly what we're doing in the reaction written this way. So zinc should be able to dissolve in a solution. So if I put a piece of solid zinc into a aqueous solution of copper, then I should be able to get this reaction to take place here. And I'm forming zinc 2+ in the process. So zinc is losing electrons, being oxidized as copper is being reduced. Now, if I think of the opposite reaction, if I said, well, why does this not take place at all? If I take the copper solid into the solution of zinc sulfate, that the issue here is that the products would be copper sulfate if they did react, and then plus zinc solid. Now the problem here is that this is less reactive than the product, so that this reaction doesn't take place. So I get no reaction when copper and zinc are added together, because it's just the flip of the top reaction. So like the top reaction, it's like it can either be spontaneous the forward direction or the reverse direction. We reasoned out that it should be spontaneous in the forward direction of zinc reacting with the copper solution to form copper solid and zinc sulfate. And if I flip that reaction, it does not take place because I'm starting with a less reactive metal trying to produce a more reactive metal. Reactions don't go that way. That's pushing the atoms uphill. Not going to take place without providing some sort of energy. These reactions are very interesting. Reactions that are, oxidation reduction, you can usually allow them to take place spontaneously in their forward direction and just plug in your charger, use electricity, then the power to go and push it back uphill. So you can usually have redox reactions go forward spontaneously, and then with electricity or some supplied energy, then go backwards in the reverse direction. Let's look at the HCl solution. So HCl, acid's right in the middle. So if I take gold, I can take anything below hydrogen and put it into a solution of H plus and shouldn't be able to have a reaction take place. So if I take gold, it's the same problem. If I take gold here into a solution of H plus, the product, if they reacted, would be H2 and gold cations. Luckily, gold doesn't dissolve in acid. Otherwise, it wouldn't be very precious as a metal because it would be reacting anytime it hit anything with a little bit of acid in it. Luckily, gold is less reactive than hydrogen, so no, the gold does not dissolve in the acid solution. I could take any metal above hydrogen on the chart. If I took lead's a good example. If I take lead solid into a solution of H plus, let's just take H plus and drop the counter ion. Well, let's include the counter ion. I guess it doesn't really make much difference if we include it or not. But we're going to have the reaction take place here because what can happen is lead can form lead 2 plus, and then hydrogen goes back to H2, and then lead pairs up with the chloride ion, so we know it should take 2 to make PbCl2. And so I'm going to need a 2 in front of the HCl to balance everything out to give me 2 chlorines, give me 2 hydrogens on both sides. And lead 0 is going to lead 2 plus, and then H plus is going to H neutral. So lead's being oxidized, hydrogen's being reduced. But the key detail here is the relative reactivity of lead. Lead is more reactive than hydrogen, so this reaction will take place spontaneously. So if I take metals above H plus on the chart, they dissolve in the solution of acid. Now, why this is important is lead piping with corrosive water that's low in pH, will dissolve the lead cation. Like, this is why lead plumbing was a terrible choice for anything used with water. Because as soon as water goes a little bit corrosive, it's going to leach out lead ions into the water. So this is why we have an issue with lead in water, is from the plumbing itself. Okay, let's end with our quiz today. We'll revisit a little bit about redox next time before we move into our final 2 sections. So we'll wrap up here today. The key word, or the code, is limiting, for limiting reactants. All right, guys, that'll do it for today. I will see you on Wednesday.